Imagine the vastness of the cosmos. Now consider the tiniest particles within it. Calculus thrives in this space between the infinitely large and infinitesimally small. It's a realm where limits reign supreme. Engineering in its essence grapples with the same fundamental forces. Whether designing a skyscraper or a microchip, understanding limits is key. Limits help us understand how functions behave as their inputs approach specific values. This is crucial for engineers as it allows us to predict and control the behavior of systems in the real world. Think of a bridge's load capacity or the efficiency of an electrical circuit. Limits help us quantify these critical parameters. By grasping the concept of limits, you gain a powerful tool. This tool helps you analyze and solve complex engineering problems. It's a journey into the heart of calculus, and it begins with a simple step. Let's take that step together. In essence, a limit is like a mathematical approaching game. Imagine you're walking towards a wall. With each step, you get closer and closer, but you never actually touch it. That's similar to what happens with limits. We look at what happens to a function's output, y value, as its input, x value, gets closer and closer to a specific number. We write this mathematically as lim x a fx equals sign L. This means as x approaches a, the function fx approaches the limit L. Sometimes, a function's value at a particular point might not be defined. However, the limit can still exist. Think of a pinhole in our wall analogy. You can't stand on that exact spot, but you can get infinitely close to it. That's the beauty of limits. They allow us to explore what happens at the very edge of possibility. Let's move from the abstract to the concrete. Consider designing a high-speed train. Engineers need to calculate the train's optimal speed as it approaches a curve. This involves understanding how the train's forces and momentum change as its velocity gets closer and closer to a critical threshold. Another example is in signal processing. Engineers use limits to analyze signals that vary over time. They might need to determine the maximum amplitude of a signal, which represents the highest point it reaches. Limits provide the mathematical framework to analyze such dynamic systems. These examples highlight how limits are not just theoretical concepts. They are essential tools that empower engineers to design safe, efficient, and innovative solutions for the real world. From transportation to telecommunications, limits underpin countless technological advancements. Mastering limits, like any mathematical concept, requires practice. Start by familiarizing yourself with different types of limits. These include one-sided limits, where you approach a value from either the left or the right, and infinite limits, where the function grows or decreases without bound. Practice solving limit problems systematically. Begin by substituting the value x approaches into the function. If it results in an undefined form like 0 over 0, explore techniques like factoring, rationalizing, or using L'Hopital's rule to simplify the expression and evaluate the limit. Remember, understanding limits is fundamental to your success in calculus and engineering. Embrace the challenge, seek help when needed, and never underestimate the power of persistent practice. The journey through calculus might be challenging, but the rewards are boundless.